Okay, so just like how we ended last class with example 6, there was like 3 different very similar integrals but slightly different. This is the same thing. We have 3 slightly similar integrals, but they are also slightly different. So if I'm looking at the first one here, I've got dx over x times x squared minus 1. Okay, anytime you see a square root in the denominator, there's either one of 2 things that are happening. Either we're going to use an arc-trig function, or we're going to have to use u substitution, right? But is this look like, or does this look like something that's over there?
Yeah.
Yes. Which one does it look like?
The
The third one. It looks like arcsecant, right? It looks like arcsecant where my u squared is equal to x squared, right? So my u value is x. And my a squared is equal to what? 1. So in this case, a is just 1. So it's literally just the arcsecant formula over there. Okay, so I can plug this values in, and I get arcsecant, because 1 over 1 is 1. Arcsecant of u, and then divided by a, which is also just 1, so I'm not going to put that, but then plus c. But my u value, I actually skipped a step there because technically, well, I wrote it up here. U squared is x squared, right? So my u value in this case should actually, instead of be u, it should be an x for the problem that we were solving, because it's in terms of x. Does that make sense? Okay, that one's done. Now letter B, similar, however, there's a variable on the top. Do any of those arc-trig functions have variables on the top? No, so we're going to have to do something different. What else could we do in order to solve this integral? U substitution. What are we going to let u equal? X squared minus 1, so that things cancel out, right? I can let u equal x squared minus 1, where my derivative then is 2x. And if I solve for dx, I get du over 2x. I like to rewrite my integral here so that I've got x dx on top, square root of u in the denominator, times my dx, which is du over 2x. What variable is going to cancel out? X's go away, and I'm just left with the integral of, I'm going to write this as u to the 1/2 power, negative 1/2 actually, times du, which then means, what else do I need to have in front of my integral? A 1/2, right? Because there's that 2 there. So if I integrate something to a power, I take that, add 1, so I'm going to have u to the 1/2 power divided by 1/2 plus what? Plus c. And if I have a 1/2 out in front and I'm dividing by 1/2 as well, that goes away, right? So I'm just left with u to the 1/2 plus c. But if I plug it back in, because I'm solving in terms of x here, my u value is x squared minus 1 to the 1/2 power plus c. Now, could I have also written it as the square root of x squared minus 1? Totally could have. Okay, last one in this kind of set here. Letter C, I've got the square root of x squared minus 1 on the bottom. Does that look like any of those over there?
The first one.
It kind of looks like the first one. However, the first one, arc sine, is a squared minus u squared, so my variable is second, right? So this variable is first instead of being second. If I rewrote it as dx over the square root, this would be negative 1 plus x squared. So that is not in the same format. We can actually not solve this with what we know so far in Calc AB, okay? This will be something that you'll be able to solve in Calc 2 or Calc BC if you plan to take that next year, but we cannot solve this problem with what we know. Okay, example 8 there has 3 integrals that are involving the natural log of x and just x. Okay, so it's not going to be any of our arctangents or arctrigs, but we are going to have to do some u substitution here. Okay, what would probably be the best thing for u to equal here for a? Natural log of x, right? Because if I let u equal x, well, the derivative of that's just going to be 1, and then I've got a natural log of x there. So that's not going to help me, right? So I'm going to let u equal the natural log of x. What is the derivative of the natural log of x? 1 over x dx, which then I could solve for dx by just multiplying by x to give me x times du. So I can go ahead and replace that stuff in my integral. So I've got 1 over x times u times x du. In which case those x's go away. And I have my integral just in terms of u. So 1 over u du, what's that going to equal? Natural log of u plus c. And then we just got to plug in my u value. My u value is natural log of x. So I've got the natural log of x plus c. All right, why don't you guys try letter B? Letter B is very similar. You're going to kind of have the same setup here. What are we going to let u equal? The natural log of x as well. And you're going to see you're going to get a different answer, okay? Did we get, when we solve this, what was the answer? Let's see. The natural log of x squared divided by 2 plus c. Yes? Sweet. Okay. And then moving on, letter C here. Letter C, very similar. However, there's no x in the denominator. The integral of natural log of x. Is that one of our flashcards? No. And we probably want to say it's 1 over x, but it is actually not 1 over x. We cannot actually solve this again. Okay. This is going to be done with integration by parts in Calc 2. Okay. Calc BC. So we got one more interesting one before we move on to the completing the square stuff. Okay, this one right here. The square root of e to the 2x minus 1. I've got a square root. Either the stuff under the square root I'm going to have to let equal u, or we're probably going to have to use some sort of arc-trig function, okay? Of the arc-trig function things, which one does it look like? Right there. Kind of looks like arc sine, right? I've got a number squared minus a variable squared. Let's see what happens when I try and manipulate this to make it look like that, okay? We have to have the variable piece squared. So how can I make e to the 2x look like something squared? What would it have to be? Like if I wanted to make e to the 2x equal something to the second power.
X equals 1.
Well, I want it to be in terms of this though. Like if I wrote this, e to the x to the second power, is that the same thing? Yeah, it is. Yeah. So I'm gonna actually do a little bit of a u substitution thing here, where I'm gonna say that u is equal to e to the x. Okay, and if I take the derivative of both sides, I end up with e to the x again times dx. And if I solve for dx, I get du over e to the x is equal to dx, right? Okay, so if I rewrite my integration here with the stuff that I've got the integral of 1 over the square root of u squared minus 1. Correct? Or my u value is e to the x, so if I square that, I get e to the 2x. And then my du over e to the 2x, or sorry, e to the x. So now I got a little bit of an issue because I've got two variables and I can't cross one of them out. So if that happens, what do we do?
Is that equal to something?
Yeah. Solve for x, right? Or solve for that e to the x piece and make it in terms of u. Well, isn't e to the x equal to u? So can I just plug it in? I sure can. So this now becomes the integral of 1 divided by, I'm going to put it over on the left-hand side because you'll see here y in a second. Now what does that look like over there for your arc-trig functions? Looks like arcsecant, right? Looks exactly like arcsecant, where my a value is going to equal what in this case?
1.
1. So I can go straight to my answer now. I've got the 1 over a, which is 1, times arcsecant of absolute value of u over 1 plus c. One last step. What do I got to do?
U.
Plug in u. So I've got arcsecant, absolute value of e to the x, plus c. Okay, so this completing the square kind of formula is up top here, except for it kind of cut some of it off. So if I have a trinomial, x squared plus bx plus c, but it's not something that I can factor right away, we can add b over 2 squared, and we can also subtract the same thing, because then I'm not really changing it, right? If I add a number, let's say I add 4 and I subtract 4, I'm not actually changing the formula, but it allows me to take these first 3 terms and factor it into this x plus b over 2 squared plus just my leftover stuff. Okay, so it allows us to integrate this a lot easier. When we were talking long division last time, long division is when we have the exponent on top is larger than the exponent on the denominator, like the power is bigger on top than on bottom, or it's the same, then we're going to use long division. If the power on the bottom is smaller and we can't do any u substitution, we're going to have to complete the square. Okay? So looking at the denominator here, I've got x squared minus 4x plus 7. I cannot factor that, right? So I need to figure out what I can add to the denominator and subtract from the denominator to make it factorable. So I'm going to take my b value, which is -4, and I'm going to divide that by 2, and then I'm going to square that. So that's going to give me an answer of 4, right? So if I add a 4 to that denominator, I can factor x squared minus 4x plus 4, and then I'm going to have stuff left over. So I'm going to kind of color code here so you see what's happening. I'm, again, manipulating the integral so that I can actually evaluate it. So this is x squared minus 4x. I'm going to change colors here. I'm going to add 4 and also subtract 4, and then have my plus 7. Okay, so now if I look at this first 3 terms in the denominator, is this something that I can factor using my, like, perfect squares here?
Yeah.
Yes, right? I can factor that into, so dx is on top. This would become x minus 2 squared, right? And now I'm going to just evaluate what is -4 plus 7. That's going to give me -3. So all I did was complete the square in the denominator. Oh, sorry, plus 3. Plus 3. All I did was complete the square in the denominator, so now I can actually solve this using things that we know. Okay. I've got something squared plus a number on the bottom. Which arc-trig function is that? Arctan, right? So let's go ahead and let u equal my x minus 2, which means the derivative would just equal dx, right? So if I plug this information in, I get 1 over u squared plus 3 times du. Now it really looks like arctan, right? Where my a value, what is a going to equal in this case? The square root of 3. Okay, so So using my arctan formula, this becomes 1 divided by the square root of 3 times arctan of u over the square root of 3 plus c. And then we just got to plug in the u. So I'm going to plug in my u as x minus 2. So I've got 1 over the square root of 3 arctan of x minus 2 over the square root of 3. All right, the difference between this one and the last one is that there is a negative leading coefficient in the denominator here, okay? Again, if I let the 3x minus x squared piece be u, then my derivative would be negative 2x plus 3, and I can't actually cancel that out with anything, right? So instead, we're going to factor the denominator. We're going to complete the square in the denominator, but I'm going to first do a little bit of algebra to rearrange some stuff. So I'm going to have 1 divided by, I'm going to have the square root of negative x squared plus 3x. Okay. Oh, and my dx there too. And then I'm going to go ahead and take out my negative on the bottom. So I'm left with x squared plus, oh, no, actually minus 3x, right? If I take out that negative. Just doing a little bit of rearranging, doing a little bit of algebra to make it a little easier on us.
That's so efficient.
Okay. Now, I want to complete the square with this x squared minus 3x piece. So if I complete the square, that means I need to have b over 2a, so negative 3 over 2, and I'm going to square that. So if I square that, what am I going to get?
6 over 4, negative 9 over 4.
Yeah, but positive, right? Because I'll square it and they'll both become positive. So 9 over 4 is what I'm going to add and subtract on the bottom there, so that way I'm not actually changing anything. Okay, so I've got the integral of 1 divided by the square root negative x squared minus 3x, and then I'm going to add 9/4. But then this is where it gets tricky. Technically, this is in the parentheses here, right? So is this a positive 9/4 or a negative 9/4? It's technically negative, right? Because there's a minus sign in front. So instead of subtracting a 9/4, I'm actually going to add a 9/4 so that I don't change the actual value of that fraction. I forgot my dx. Now on the bottom, I can actually factor that. Okay, so this becomes the integral of 1 divided by the square root of negative, and this will be x. And remember, this value right here that you square is actually going to be with your parentheses there, so it's going to be minus 3/2 squared is equivalent to this piece right here. Okay? Yep. And then I'll have that plus 9/4 on the outside. And now if I look over at my arc-trig functions, which one does this look similar to? It's not going to be arcsecant because I don't have a variable on the outside, right? It is going to be arcsine. I'm going to manipulate this equation again a little bit to make it look like that, okay? So I'm going to rewrite this with 1 over the square root. I'm going to write my 9/4 first. And then I've got minus my x minus 3/2 squared. Okay, so this is my a squared piece. This is my u squared piece. Do we see that? Okay, so I can go ahead and do my u substitution now. So u is equal to x minus 3/2, which means my derivative is just dx. So when I take the integral, I've got 9/4 minus u squared du. Now, if my a squared is equal to 9/4, what is my a value going to equal? 3/2. Okay, so using my arc-trig function, arcsine, this is going to become arcsine of u divided by a plus c. But I can simplify that u over 3/2 piece. So our final answer is arcsine of 2/3. But then my u value was x minus 3/2. And then plus c. Okay. Again, sometimes we can manipulate an equation by just adding or subtracting one number. Okay? If I look at this fraction, the numerator is not bigger than the denominator, so I'm not going to do any sort of long division. Okay? I also have variables in the top and the bottom, so usually in that case it means you probably aren't going to do the completing the square piece. But what we're going to do instead is if I let u equal x squared minus 2x plus 3, what is the derivative of that going to give me? 2x minus 2, right? Times dx. Now, 2x minus 2, well, that's a really big number because I have 2x minus 1. Okay? But I could take and subtract 1 and make it negative 2, but then I also have to add 1. Okay? Which again seems kind of silly because you're not going to simplify it right away, but you're still adding 0 basically. Okay? So I'm going to go ahead and solve for dx. So I've got du over 2x minus 2 is equal to dx. And I'm going to show you how I can actually change this integral. So I'm going to rewrite this as the integral of 2x minus 2 divided by x squared minus 2x plus 3 dx. That is technically all of this stuff. Okay. And then I have a plus 1, but is it just plus 1 plus the integral of 1? Or is it 1 over all this stuff? It's 1 over all that stuff, right? So then I'm going to have plus the integral of 1 over my denominator. Are we okay with how I split that up there? Okay, because now that first piece there that I highlighted in red, we can actually use u substitution and evaluate this integral. So let's finish that one out. If I plug in that stuff, I end up with 2x minus 2 over u times du over 2x minus 2. So the 2x minus 2 goes away, and I'm left with the integral of 1 over u du. And what's the integral of 1 over u? Natural log of u. Okay, that piece in blue can I use u substitution here? If I let u equal same thing, I'm going to have 2x minus 2 on top. Is that going to cancel out with anything? No. So instead what we're going to have to do is we are going to have to complete the square for this one. Okay, so in the denominator, this is going to become 1 divided by x squared minus 2x. And then my b over 2a. What's my b over 2a value going to be squared? 1, right? So I'm going to add 1 to this and subtract 1. And then I've got my plus 3. Okay, so I'm completing the square for my second integral there. So now these first 3 things we can factor, and it's going to become 1 over x minus 1 squared, and then negative 1 plus 3. What's that going to give me?
2.
Yeah, so plus 2 on the outside of that factor. So I can let u equal my x minus 1, which means my du is just equal to dx. So when I replace those things, I have 1 over u squared plus 2 du. Now it looks even more like arctan over there, where my a value, what's my a value going to be?
Square root of 2.
Square root of 2. Okay, so this is going to equal 1 over a, so 1 over square root of 2 times arctan of u over the square root of 2 plus c.
Two different u's.
I do. I should have probably evaluated that before. I was just looking at that. So I need to plug in my u, which is equal to x squared minus 2x for this one. And then on this side, my u is equal to x minus 1, and I should plug that in there. So yeah, I probably shouldn't have written it like that, but that's okay. We're gonna finish it out. So I've got the natural log of x squared minus 2x plus 3. And then plus, I don't need to rationalize anything, so 1 over square root of 2 times arctangent of x minus 1 on top, square root of 2 on the bottom, plus c. Okay, so there will be one like this on your homework that you will have to add and subtract a number to, so that way you can actually evaluate this by hand.